Okay, so we're just talking about, back in the days when I played golf in college. I once hit a ball into orbit, I think. We never could find it, and I figured that's where it went. Okay, so just try to figure out what it takes to get something into orbit. To orbit, you gotta be at least 200 miles above the Earth's surface. And that's not gonna be a very stable orbit. You're gonna have to boost it a lot because there's some stuff out there. If you want an orbit that you don't have to boost very often, you go with that. Okay. Anyhow, 200 miles. 200 miles, about 320 kilometers above the Earth. To get the golf ball up there, I'd have to supply enough kinetic energy. Okay. To overcome the potential energy gain, or to accomplish the potential energy gain. What's potential energy change from here to up to 200 miles? That's pretty simple. First of all, you can't just use MGY or MGH or whatever, okay? Because G isn't constant, it's decreasing as you go further from the center of the Earth. Saw that last time. Okay, well, on the other hand, we're only going about 1/20th times the radius of the Earth further from the center. It's only 5% further. If you do an inverse square of 5% further, you're doing an inverse square like of 1.05 times RE. Well, square of 1.05 is about 1.1. Reciprocal 1.1 is pretty close to 0.9. So, you're still going to have 90% of the pull of gravity at that distance. Now we can be more accurate, and we will, and it's really easy to integrate the universal gravitation. Just you're integrating 1/r squared with respect to r. Duh. Antiderivative of -1/r. It's not difficult. Okay. And we'll do that. But right now we're just doing a ballpark estimate, just to see what the probability is that that ball really went into orbit. Okay. So we're going to need a kinetic energy to overcome the potential energy gain. Well, just taking account of a couple of things. If we approximate using 10 meters per second squared for the whole distance, we get about 3.2 million joules. Joules per kilogram multiplied by the mass. Okay. So the potential energy you need to get up there is about a kilowatt hour per kilogram. That's like 10 cents worth of electricity. Who's going to spend that to get something in orbit? Well, yeah, okay. That's a pittance. Now, of course, I'm ignoring the fact we've got to go through the atmosphere, and the atmosphere is going to pretty much prevent us from doing it anyway. Okay, if the atmosphere wasn't here, well, then it'd be really hard to hold my breath long enough to hit the ball before I died. Okay, and I'd swell up, and it'd probably have less efficient golf swing and stuff like that. So I'd probably never do it. Okay, now, what kind of energy, what kind of power do I have to produce in order to just produce 1 kilowatt hour of energy? Okay, well, it's like 3 million joules. Okay, well, let's see. Got to do that in the time it takes to swing a golf club. It's probably a second or less. So that means I've got to be working at the rate of about 3.2 million watts. Okay. I'm not sure which part of my body that's going to strain the most, but I'm thinking these muscles along here as I start to downswing. Okay. I'd rip myself apart. Okay. 3.2 million watts. I maxed out at being able to produce 300 watts. Or about 4 watts per kilogram. Okay. And I don't have that many kilograms. At 4 watts per kilogram, I'm not going to get up to 3 million watts. And that's just the energy that would go into the ball. The energy I need to move my body and the club and everything is much greater than the energy that actually goes into the ball. So for that reason, I have to draw the reluctant conclusion. I'd probably just knock the ball into the woods or something. Okay, never found it. Can't prove that happened, but it's likely. Okay, now of course, if I want to go on TikTok and find somebody that tells me I really hit the ball into orbit and believe that I can do that. Okay, People believe even more ridiculous things because they see them on TikTok and they want to believe them. But forget that. Okay, talk about critical thinking. So that's all I'm going to say about it. Okay, so that's not going to happen. Now let's get serious and think of how much energy it takes to get a satellite in orbit. Okay. Now, satellite doesn't get into orbit by itself. The satellite is a little tiny bit of the mass of this huge rocket, or this large rocket. You can't get to orbit with a small rocket. You know, relatively small compared to Saturn, but still a pretty big thing. You can't really bench press it more than 3 or 4 times. Okay. Even when it's not full of fuel, which is what it's really heavy. Okay. So not only do we have to get to the 200 miles, if we go up there 200 miles and say, okay, we're in orbit, well, it's just going to drop straight down. How do you get it in orbit? You got to give it enough speed. Okay, well, the criterion for orbit, circular orbit. Okay, what can you tell me is necessary for circular motion? Okay, well, the condition for a circular orbit, for any motion in a circle at constant velocity, in a circular orbit, your speed would be constant and your centripetal acceleration would be v squared over r. Okay, so you're up there 200 miles and you got to give things some speed. Okay, and v squared over r, where r is your distance from the center of the earth, multiplied by whatever your mass is, gives you the force you're going to need, right? Or the force you're going to have, because, well, you're going to have to match up your velocity with r. So the question is, where does the centripetal force to put a mass into circular orbit? Where does that centripetal force come from? Okay, well, the process, so we've got a pretty good discussion. You know, somebody talking about in a NASCAR wreck, car spinning real fast. You know, people tend to survive those crashes because they have good roll bars and helmets and restraints and stuff like that. So they usually just walk out, take off their sunglasses, you see if their eyes are all bloodshot. So speculation, is that the centripetal acceleration? Now, when the question was first asked, I thought you were talking highway speeds and I couldn't see. Because, you know, thinking 2 meter radius of rotation at 30 meters per second, about 70 miles per hour. I don't think you're going to get that at highway speeds. In a NASCAR 200 miles an hour, yeah, I think that becomes more or less feasible. And that would give you centripetal acceleration, 30 meters per second, 2 meter radius of 450 meters per second squared, was 45 Gs. I don't know that you would actually get 30 meters per second. You wouldn't need all that. End up with bloodshot eyes. If you got the 450 meters per second squared, I don't know if you could spot that, even though it's only for a couple of seconds. I don't know. And so I think it would be somewhat lower than that, but yeah, I can see where you could get that kind of centripetal acceleration that would cause the eyes become bloodshot. Okay, well, that's good. Intuition around centripetal acceleration. Now let's apply that to the Earth, because what we concluded was the centripetal acceleration you need to stay in a circle around the Earth has to be coming from gravity because there's nothing out there acting on you. Okay, so Centrifugal force comes from the Earth's gravity. So the magnitude of the centrifugal force from the Newton's law of universal gravitation we talked about last time is just this. Okay. Now, also, if you are in a circular orbit, you are at constant velocity, and centrifugal force is m v squared over r. The big G, big M, little m over r squared equals mv squared over r. Okay, go ahead and get your expression for v. Got an equation, solve it for v. Okay, we just do the algebra here. We get v equals the square root of big G, big M divided by r. Now, implicitly, big M is the mass of the Earth. Okay. So we could put numbers on it. Mass of the Earth is real close to 6 times 10 to the 24th kilograms. Radius of the Earth is about 6,340 kilometers. Depends on where you measure. It's kind of flattened at the poles. Okay. So it kind of depends on where you are. It's in the 6,300 and some, though, just about everywhere. Okay. So well, I'm going to overestimate it. As 6,400 kilometers, it's actually about 1% less than that. Okay. It's about a 1% overestimate. And 6,400 is just a rounder number than 6,300. 6,300 is probably closer. And I just like to work with numbers that are easy to work with. Okay. Well, and G, I said what it was last time. I never wrote it down. How do you think? Actually, I think I did know. Oh. Okay, there's your value of G. So it becomes pretty easy to figure out the speed of your orbit. You're not going to do that. You just plug it in. Any fool can do that. Okay. Got to be a special kind of fool to be an engineer, not something. We got to work on that. Okay, so what's the kinetic energy? Well, kinetic energy is implicitly this kinetic energy from mass m in orbit at whatever distance. And notice that V is the same no matter what the mass of the particle is, okay? And it depends only on the radius of the orbit. So we do 1/2 mv squared. And then we got the kinetic energy of a circular orbit. Okay. What's potential energy? Now, for you, Bill, I calculated the potential energy change from the surface of the Earth to the orbit, right? When we're doing potential energy in this context, we do it with respect to infinity. Okay? Because we get a simple result. So then we'll worry about the sign of it. Right there's your force. You're integrating your force with respect to your position. Okay? Turns out it doesn't matter what path you follow because gravity is a conservative force. Now we'll prove that in general by showing that it's a gradient of a scalar when we figure out what a gradient of a scalar is, which will be along about February in molecular calculus. Okay. And it's not particularly difficult calculation, but there are a lot of fairly challenging ideas around it, so we'll save it. Okay, so here we have it. Now let's just draw a picture because pictures are always great. Okay, here's your planet. Pass M. Let's take a path from the center of the planet. Let's take a path away from the center of the planet. Is gravity going to do positive or negative work along this path? I think somebody went like that. That seems like a pretty negative comment. So yeah, I believe you. Okay. Yeah, it is. Because you're going this way and gravity's pulling you this way. So gravity does negative work. Okay, so now this is an arbitrary path. The center of the planet to infinity. Okay. We don't want to try to integrate over this whole path. We don't want to try to figure out the potential energy over this whole path because it'd be infinite if you assume all the mass of the planet was concentrated at the center. But it isn't. So that the gravitational pull between here and here is variable in a way that depends on the relative density of different layers of the planet and so forth. Okay. Anomalies, different planets would be different. And we aren't even sure really what it is for our planet, although we've got a pretty good idea. So it only makes sense to integrate from some point above the planet to infinity. Okay. So we're going to go to some distance. R sub 0, R naught. Okay. That's here. And we just take this part of the path. we integrate from R naught to infinity. Now, what do we integrate? We integrate the gravitational force. Now, here's where it gets a little confusing. It's just a matter of keeping track of signs, what's positive and what's negative. Okay. If we integrate from R naught to infinity, we get the work done. On the mass, this goes from here to there. Okay. So that the work done what we're going to get. Okay. First place, when you integrate 1 over r squared, get negative 1 over r, you're just going to get big G, big M, big little m over r, which is a whole lot like this, except that I'm pulling left and 2 off here. You guys had it, I didn't. Okay, get that 1/2. Okay. We understand if you integrate this with respect to r, you're going to get big G, big M, little m over r. Okay, that's going to be your expression for the potential energy, except it's going to be negative. Okay. Now, intuitively, your potential energy increases as you go from here to there. Okay. Well, if you're integrating relative to infinity, you think of going from infinity to here. Makes sense? If I want to integrate the force between here and there, my integral goes from here to there. If I want to integrate the potential energy relative to this point, that's what I do. I go from here to there. Okay. Anyhow, think it through. Potential energy relative to infinity is going to be this integral. Well, let's do the integral of I'm just trying to decide where to put my negative sign. Okay. I'm going to go from infinity to R naught. And then I put a negative sign here. Because gravity is a force of attraction, gravity is pulling in this direction. Okay. So according to this, I'm going in the negative direction from infinity to here. Okay. And gravity is pulling in the negative direction. Actually, I just confused myself. What that negative sign? Anyhow, yes, I do. No, I don't. Gotta be given negative. That's gonna be negative. Yeah, I do. Yes, I don't. No, yes, I do. Okay. It shouldn't confuse me. Should have thought this through a little better before I started to explain it. What you get is big G, big M, little m over r is the integral of negative 1 over r squared is a negative of negative 1 over r. Antiderivative of 1 over r squared is negative 1 over r. Everything else is constant. Okay. And this is evaluated from R naught. Well, between R naught and infinity, like this. I shouldn't have the negative there. Well, I've got it. It's like this. Okay. And debating about whether what's a negative sign there or not. I'll explain it in a minute. Okay, so actually, this would be negative, this would be positive. Anyhow, you get negative big G, big M, little m over R. And there's your potential energy relative to infinity. Now we apply that. Total energy orbit is kinetic plus potential energy, which is one half big G, big M, little m over R minus big G, big M, little m over R. And what's that? It's this. Okay. Its magnitude is half the kinetic energy, but it's negative. Now, why is it negative? Well, because of the integral that I confused. But yeah, we'll straighten that out at some point. I want to move on with this. Okay. Here's one circular orbit. Here's another circular orbit. So let's say this is at R1. And this is at R2. Okay, before I go on with that, let me correct one thing over here. This is over R naught. That if your orbit is at distance R naught, there's its potential energy relative to infinity. So if this distance is now R instead of R naught, we have this. I want to distinguish R naught from our variables integration. I don't want to use a dummy variable. Okay. I hope you understand what I just said, but there it is. Okay. So which orbit has the greater energy? Okay, we're trying to reason this out just by various forms of intuition, which you really want to do. You want to reconcile your intuition. So that's exactly what I want you. But right now, thinking is a little convoluted on it. And I always found it confusing. Okay, it just didn't seem intuitive to me until I worked with it a lot. Okay, but there's a simple reason for the answer. But we're not going to do the simple reason. Okay. First place, the kinetic energy is greater here than it is here. Okay. Your potential energy has a greater magnitude here than it does here, right? Okay. But of course, your potential energy is negative. So the question is, what has greater magnitude, potential or kinetic? Okay, well, the potential has greater magnitude. Just look at what we just derived. You know, kinetic is a 1/2 big G big M over R. Potential is a complete big G big M over R. It has greater magnitude, but it's negative. Okay. So you've got a bigger kinetic energy, but you have to your potential, your total energy here. Well, let's talk about the potential energy. your potential energy is greater in magnitude, but it's negative. Okay, so you got a lot of potential energy, but you also got twice that much negative potential energy. So your total energy is the negative of your kinetic energy, and your kinetic energy is greater here. So you have a greater negative here than you have here. Now, which is greater? Bigger negative or lesser negative? Okay. The lesser negative is greater in the sense of the greater than sign. Magnitude is less, but it's greater. Now you can think through all that, or you can just look at the expression, total energy. R is less, then your negative is greater, right? I'm telling you, you're taking the negative of a bigger thing. Okay. If R is greater, you're taking the negative of a smaller thing. Well, the negative of a bigger thing is less than the negative of a smaller thing. You can reason it out that way, or you can write an equation. Take this versus this. Okay. And I'm climbing this back. Can we verify this? That inequality tell us that R1 is less than R2? Well, we can divide out the 1/2s and the big G's and the big M's and the little m's, right? And we get -1 over R1 is less than -1 over R2. Now, does that tell us that R2 is less than R1? Intuitively, maybe it should. Let's multiply both sides by a negative. That reverses the inequality. That is a very simple step. Get R2 is greater than R1. Okay. So pretty much nails that the total energy at R2 is greater than the total energy at R1. Because both are negative, and each is equal to the negative of the kinetic energy. So the negative of this greater kinetic energy is less than the negative of this lesser kinetic energy. Okay, all kinds of ways you can do it, but that's intuitively not real clear. If you go to atomic structure, orbitals and all that stuff, you've had chemistry, haven't you? Okay, I don't know how deep you went into orbitals and stuff like that, but you go from the lower orbital to higher, you got to add energy. Has greater potential energy here. As we see in physics, if an electron falls from here to here, it loses potential energy. And that loss of potential energy has to go somewhere. It goes into electromagnetic radiation typically. Okay. So, yeah, that's another connection. So this whole thing about, you know, how the negative total energies relate, it's a little hard to really resolve with everything. You saw me get screwed up over here. Okay. So the amount of energy we need to add to whatever satellite we want to put into orbit is the change in its gravitational potential energy. Okay. Plus change in its kinetic energy. If we want to go from one orbit to another, how do we do that? Well, we're in an orbit here. We want to go into an orbit here. We don't just turn our steering wheel and drive out there. Yeah. Turns out we have to spiral out. Now, one way to do that is kind of interesting. One simple way to do that is we just go to this point and we fire our rockets to give us more velocity, and we need to stay here. That moves us out of our circular orbit. It actually moves us into an elliptical orbit. Something like this. Okay. When we get out to here, we hit the gas again, give ourselves enough velocity, stay in this orbit. That's one way to do it. Got a question? No, I wasn't very careful. I wasn't thinking when I drew this. Energy is not conserved in this orbit because you have more energy here than you have anywhere on the circular orbit, right? The way I've drawn it, you come into something like a circular orbit here. Okay. So in here, you got less energy than you have here after you give it the boost. So what really happens is your circular orbit comes in and it's going slower when it gets out here. So it falls in closer. When it falls in closer, it picks up more speed. So it's going much faster here than it was going here. Okay. So the total energy stays the same. And that's kind of important. The other thing that's important, I'll just lay this on you, since we just talked about angular momentum. Here you got the sun. And here you got a comet. Comet has a circular orbit around the sun. The force exerted by the sun is always toward the sun. Okay. Which means that the torque exerted on this thing about the center of the sun is zero, because the moment arm is zero. The sun's on the path of this thing. Remember what we did last time. Okay. So at no point on the path do you have any torque. Which implies constant angular momentum. Okay. Which tells you, as Kepler said, that in equal times, you sweep out equal areas of this orbit. Okay, so we'll make more sense out of that next time, but understand this one thing, that if the sun is producing the force, it's not producing the torque. It's a force of attraction from there to here. There can't be any torque. And if there's no torque, you can't have a change in angular momentum because of the impulse angular momentum theory. Okay. So you're probably gonna want to know that, do some of the homework. I don't know if you're gonna get to it in this assignment, but you're gonna need to know it.